So we now move to the next chapter of this book, Quantum Optics by Mark Fox. Chapter 2 was classical optics. Chapter 1 was just introduction of how to use the book and what the book is about. And chapter 3 now we have is on quantum mechanics. So quantum optics is basically applying quantum mechanics principles to the field of optics. So in order to have a good understanding of quantum optics, you should be aware of the basics of both optics, classical optics, as well as quantum mechanics. And that's how this book is structured. So first we had a look at concepts of classical optics, and now we will look at some elementary principles of quantum mechanics, and then slowly we will build on these two ideas and concepts and then move into quantum optics. So the first question of this chapter is problem 3.1. It says, use the orthonormality condition of eigenfunction wave functions to prove equation 3.24. And just for you, I have written down equation 3.24 of the book over here. So this is summation over n of mod Cn squared equals 1. And we need to prove this equation. Now, I need to provide some context of this equation, what this equation means and from where it comes and what is the background and context of this equation. For that, we need to look at Schrodinger equation. So I'll write down the Schrodinger equation. So Schrodinger equation is given as follows. So this is the Schrodinger equation. Here this h hat, h cap or h hat you can call it, is called the Hamiltonian operator. R is position, t is time, and this del by del t is partial derivative with respect to time, and psi is the wave function. So this is the wave function, and Schrodinger equation basically describes the physical state of a particle in any given quantum system, and this is given by the wave function, and the equation of motion for this wave function is the Schrodinger equation. So in quantum mechanics, the wave theory and particle theory are combined together by wave particle duality, and this wave function is associated with each particle, and using this wave function one can extract various physical measurables. So that's the Schrodinger equation. Now this wave function can be written down with time part and space part separated out. So if we look at, so this is the wave function, and we can then separate out the time part and the space part. So let me just write it down. So this is the total wave function which has the space and time parts both together. We can write it down as follows, with the time part and the space part separated. So this is the time part, and this is given as exponential of minus I e t over h cross. And using this, the Schrodinger equation can then be reduced to time independent Schrodinger equation, where we treat the time part separately as this, and then the Hamiltonian acts on the space part. In this way. So here then this E is En, and this is the psi n is the eigenfunction of the Hamiltonian operator. The index n basically denotes the state of the and the quantized level of the particle. So En means the energy of the nth state. Now, the orthonormality condition, since we need to use the orthonormality condition, let me write down the orthonormality condition also. It's given as follows. So if you take two eigenfunctions, psi n and psi n prime, and integrate it over all volume, take the product as follows: psi n star psi n prime, then this integral equals delta n n prime, where delta n n prime is the Kronecker delta function, and this is 1 if n equals n prime and 0 if n does not equal n prime. So this delta n n prime is known as the Kronecker delta function. Now where do these Cn's come from? So let me write down what this Cn means. So what we can do is we can have the wave function written as a superposition of its eigenfunctions. So any state, so this is a superposition state. So any random state at time t equals to 0 can be written as the superposition of its eigenfunctions. So this is superposition, which is basically the linear combination of the eigenfunctions, and then at any particular time t you will have the time part multiplied times this time part. So this is the time evolution of the wave function. Now using this so Cn is basically the coefficients in the superposition. So now let us write in shorthand notation. So this psi is superposition of the eigenfunctions. So psi star psi, if we look and if we integrate it over entire volume, this can be written as follows. We will make use of this orthonormality condition. So this is basically integral of psi star is Cn star psi n star times psi. So that is another summation Cm times psi m, and then integral over the entire volume. And this can be rearranged. We can take the summation out and the integral goes in. Cn and Cm are complex coefficients. They are just numbers, complex numbers. And then these eigenfunctions integrated over the entire volume. Now, so I used superposition over here to come to this step, and now I will use the orthonormality condition. So first I made use of superposition from here to here, from first step to second step. I used superposition principle, and now I will use orthonormality condition. So this becomes, this simply becomes delta n m by making use of the orthonormality condition. Now because of this Kronecker delta function, one summation gets reduced because n equals m, only that time we have the value 1, and for n not equal to m, Kronecker delta function is 0. So it picks out a value of 1 only when n equals m. So we have Cn star Cn, which is nothing but summation of n mod Cn star. Now this left hand side part, this is by definition 1 because of normalization. So by definition this is 1 because we know that for a wave function, for any wave function, what we have is mod psi squared d cube r over the entire volume is equal to 1. This is for any wave function for any physical system. This is the normalization condition, and thus we get our desired result, that is summation n mod Cn squared equals 1. So hence proved, we have completed the first question. So the important concepts in this problem were Schrodinger equation, the eigenfunctions, and superposition principle.